Hi everybody, welcome back to Chem 121. Today we are going to be working on Chapter 9, and it's one of the last two chapters in the class, so we're almost there, actually, believe it or not. Some important things to note. There's a bunch of stuff due tonight and tomorrow, so make sure that you are getting all these things in by their respective deadlines. Quiz number 7 is due today by 11:59 p.m. Quiz number 8 and the lab worksheet for this week are due tomorrow. Those are all soft deadlines, so if you need an extra day for quiz 7, get in by tomorrow. Don't take too long, though, because the other two assignments are waiting too. Thankfully, next week won't be as bad. You'll just have quiz 9 due next week. Okay, let's get the show on the road to Chapter 9. Chapter 9 is all about different types of reactions and different properties that we can measure of them with regards to energy and speed. Oftentimes, it is in our interest to have a reaction that either generates lots of energy or doesn't generate a lot of energy, or goes really fast or goes really slow. If we can understand how we control those types of reactions from a general perspective, then we can apply those concepts when we get to biology. So, for example, in cell bio, most reactions that occur in the body are really, really, really slow. In fact, they're too slow to sustain life. And so we need to do stuff to speed them up so they can occur at a reasonable temperature, reasonable being body temperature, and a reasonable speed, which is how fast we need to make it as opposed to how slowly it normally would occur outside of biological conditions. So we're going to talk about all of those things that will set you up for cell bio in this chapter and the next one. The next chapter is pH, so it's just the other half of what we're doing here. So we're going to study 5 different types of reactions. I'm going to go through these kind of quickly because they're not super important. Combination reactions combine things together. Decomposition reactions break things apart. So these are essentially opposites of each other, these two. Single and double replacement reactions require you to swap one thing. So single is swap. That was supposed to be a W, but my pen jumped there. So single and double replacement are switching out one or two things in a reaction. And then combustion is a special category of reaction that just anything reacting with oxygen is combustion. So this one's kind of unique in the sense that it can be, the other things can also be combustion, but a combination reaction will not be a double replacement, for example. So the first 4 are pretty much all mutually exclusive, but combustion can be applied to a few of these, not all of them based on their definitions. So we're going to go over some examples here. But this is mostly just an exercise in, match the reaction, and we could totally do that. So on the screen, you'll see a combination reaction. Putting 2 products together to make two reactants together to make one product is a combination reaction. And so I have some examples of that down here. And you can see that I'm just combining this thing with this thing to get this thing. Now, these reactions that I picked just happened to be, I just stick the 2 things together. But this, for example, is also a combination reaction. I just need to balance the equation when I'm done. And so what's important is that I combine the first reactant with the second reactant in whatever ratio is necessary to get the product, and that the product is just a combination of those 2 things. Those 2 elements, that is. So if you have like Cl2 or O2 or N2 or whatever as a reactant, you can still be a combination reaction. Okay? So just be mindful of that you're not just looking for literally OA plus B equals AB. Because there is a little bit more nuance than that. Now, for a decomposition reaction, you're doing the opposite. Whatever my react, those are calcium carbonate compounds. Limestone is this thing. And if you pour acid on it, it'll start bubbling. You'll get calcium oxide and CO2. We'll talk about the effects of acid in Chapter 10 when we talk about acid rain and things like that. Carbonic acid is another common one. This is what makes your fizzy drink fizzy. When you put CO2 into your water, it combines to make carbonic acid, which is why you taste the tartness of carbonated water. But as the solution goes flat, that is because the dissolved CO2, or carbonic acid, decomposes into just water and then CO2, and this is a gas, which bubbles up out of the can, or the soda bottle, or whatever carbonated beverage container you have. And eventually all you have left is water with flavoring in it, and then it's flat, and then we don't like it, and we pour it out, right? Here's another example. Potassium chlorate can be decomposed into potassium chloride and oxygen. And really, all we're looking for is that these two things, when we combine them together, we will get this thing. Now, the form that you see it in might not match up with what we would predict. So, for instance, we have a KCl over here and we have an O2. So you might predict KClO2. But really, we're just looking for KCl's and O's. And whatever ratio those fit into is fine. It's still a decomposition reaction. So for this first type of replacement reaction, the single replacement reaction, we're going to swap one element for another in one compound. So here's my one compound. And I'm going to swap A and B. In a double replacement reaction, I would have two compounds and I would swap A and B in that case. So I'd have A paired with Y, for example. Now, this commonly happens in reactions that are called redox reactions. We're going to talk about redox reactions very briefly. But the most common instance of a redox reaction would be a thing like a battery. So in a battery, we oftentimes have a metal electrode and then a solution, and we do a single replacement reaction in order to generate a current. Now, the reason that a current is generated is because we're actually changing the charges on all of these substances that are being replaced. We're going to talk about that in like a few slides, so I'll save that for then. But for now, when you're looking for single replacement reactions, you should be looking for something by itself that then swaps into a substance that gets traded out with it. So that other thing is now by itself. So here's some examples. Oops. I already had one example on the board there. There's another example. So here, my fluorine goes over here and swaps out with chlorine. And it does this. Now, notice how I have F2 going in, and it only becomes F because there's the 2. And I only have one Cl coming out, but it becomes 2 because I do have 2 chlorine. Okay? So, again, don't let the balanced equations trick you into thinking, oh, this isn't a reaction type I know at all, when it totally is. All right. For the double replacement reaction, we're going to swap both compounds here. So here's the first compound, here's the second compound. And I'm going to swap A and B. Now, a way that you can imagine this is that you have two dancers, or two pairs of dancers. So here's my two dancers, and here's my two dancers, and they're holding hands or something. And then what this one does is now this one's going to trade to this person, and this one's going to trade to this person. So that now this is going on. And in the reaction, that's exactly what happens, is I'm just trading A and B, and X and Y remain stationary. And so I'll just fill in the letters here so that you can see how that worked out. There you go. Now, these are a little more obvious to see because really you're just looking for, okay, I'm going to just swap either the first thing. So now I should have NaNO3, which I do, NaGCl. Or you could even swap the last things. And either way it works. So if I wanted to switch these two instead, that would also work. So you have options for double replacement. Just switch one of the two. Either the front ones or the back ones. Now again, when you do this, your coefficients might get rearranged. So I have 2 total potassium. I have 2 total potassium. But each potassium is K+. So in both cases, it remains the same. So be mindful of that when you're doing these reactions. That again, yeah, watch out for the coefficients. That's just so the reaction remains balanced. Double replacement reactions are not redox reactions. And we'll show why that is in a little bit. The last type of reaction is combustion. Combustion is just, hey, does it react with oxygen? If you see oxygen in there, it's a combustion reaction. And that's really all you need to know, is you just need to see, oh, there's oxygen there. There it is. Combustion. Wow, my pen did not like that. Okay, hold on. Sorry, I went to circle the oxygen and, like, it jumped over to the side or something. The cursor, not my actual pen in my hand. There we go. All right, I'm going to put a bunch of these on the board here. Oh, I forgot that we're talking about CHO here. Now, if you combust a compound and your compound contains only carbon, hydrogen, and oxygen, the oxygen is optional. But if you only have carbons and hydrogens, the only products you get out are CO2 and water. So on the top there, I have the combustion of hexane. Hexane is a solvent that is used in industry and chemistry. If you burn it, you get CO2 and H2O. On the bottom, I have ethanol. Your body tries to combust ethanol through respiration. So you get ethanol from whatever source, so like whatever liquor or booze you're drinking. And then you inhale oxygen. And then in your liver, it reduces or it oxidizes the ethanol to CO2 and water and breaks it down. And then you breathe the CO2 out. You get to keep the water. Now, there are intermediates on the way for the combustion of ethanol. It's not as simple as this reaction because you have to go through like acetaldehyde and stuff like that. But overall, this is the reaction and the end results for the combustion of ethanol specifically. So I'm going to give you these reactions on the board here. And what I want you to do is I want you to give each of these a category. Or if there are multiple categories, give me both. Remember, combustion can be applied to any reaction. So list these out in the chat. Just number them 1 through 4. And we'll go over the answers in just a bit. 1 or 2 more minutes, we'll go over the answer. All right, let's look at these. So, for the first reaction, and I always try to like give you a chance to like devise your own strategy here. But the way that I look at this is the first thing I look for is how many reactants are there? And if there's only ever one reactant, then it has to be decomposition. And so this split into 2 pieces. So there you go. Now this second reaction, I have something by itself and then a compound. So you look at this and you might think, okay, single replacement. This is probably a good single replacement. But then over here you see, oh, wait a second, it's all paired. Well, I just swapped the order on you in order to try and like hide it. I'm trying to obfuscate this just a little bit. And you'll see that, oh, I have H, an element by itself. So did I swap Mg for H? And the answer is yes. Yes, I did. So this is a single, not a cis. I swear, sometimes I just start writing random shit and I don't know. My brain just wants to write words. It doesn't want to, like, stop. I don't know. For the third one, I have something and something else being combined, so this is a combination. However, the thing it's combining with is oxygen, so it is also a combustion. And you might think, well, that's weird. Can I combust a metal? Yeah, you could absolutely combust a metal. And then finally, for this one, I have sodium paired with hydroxide and hydrogen paired with chloride. And if I swap these two, then I get HOH and NaCl. Well, HOH is actually H2O. So this is a double replacement. It is not a combustion, though, because we're not reacting it with oxygen. We're reacting it with hydroxide, and that's different. Combustion is specifically oxygen, O2. There you go. Those are the types of reactions we're going to look at in this chapter. We're probably not going to refer to them by these names very often, but just in case the names come up, we'll talk about them then. We are going to spend a little bit on redox reactions. We don't really cover these in the detail that is in the text. And for good reason, because redox reactions are kind of complicated. And there's a lot going on. So what I'm going to do is I'm going to actually show you the complex version, and then we're going to sort of ignore it and try and just like find shortcuts and stuff. So what is a redox reaction? A redox reaction is any reaction where not only do you move around elements to make new things, but you also have to shuffle around electrons. Now, we've sort of ignored electrons in these balanced reactions, right? All we've been doing is balancing the equation to make sure that the number of elements on each side is the same. But it turns out that for some reactions, electrons get moved too, and we just don't realize it unless we look at the substances in more detail. And so I'm going to look at these in before and after terms. So the first thing we need to do is define the terms, and then we're going to apply before and then after. And the term will be that we're going to apply, oxidation or reduction, is going to be what happened before and after. How did it change? So let's look at these two terms. The first term is oxidized. If something is oxidized, it means that we are taking away its electrons. And this is the weird part. If something is reduced, it's because we're giving it electrons. Now, you might look at that and think, well, wait a second. If I'm reducing it, why is it gaining electrons? Because electrons are negative. What we're reducing is its charge. We're making it more negative. Now, how do you keep this straight? And the answer is oil rig. And so if we write the first letter of each of these, and you probably see it up above, it's all highlighted, right? So oxidation is losing electrons, and then reduction, I'm trying to write sideways, my goodness. And now I have to sneeze, sorry, hold on. Okay, I think I sneezed off the mic, that's good. You know, let me just erase this, and I'll just put it right here. So, oxidation is losing electrons, that's the oil part. Reduction is gaining electrons, that's the rig part. So remember oil rig, and then you'll always remember which one is which. When it comes to oxidation and reduction. Okay, so now that we've seen what the terms are, let's look at some equations here. I'm going to just put oil rig on the screen here so that we have it. And then this didn't show up because I did maximize it first. So there it is. I'm going to give you a reaction that we just looked at. In fact, let me go grab a specific reaction that we did do. Yeah, let's do this one. So on the previous slide, when I asked you to categorize reactions, I gave you this. And I got to balance the equation here. So there we go. So what we're going to do is we're going to look at all of these things and consider their charges. Now, you have to be very careful here because there is a tendency for students to go, oh, whenever I look at magnesium, it's +2 because that's how it gives me the octet rule, right? And that's correct, but remember, this is only true if it's in an ionic compound. Right? If I went over here and I asked you what the charge of this magnesium was, you can't say +2, because if you did, we'd have an issue. There's nothing written there, right? This is just magnesium metal. So if I write an element by itself, its charge is 0. And we know that has to be the case because a neutral element off the periodic table has the same number of protons and electrons, right? We covered that in like chapter 3 and 4. That was way back, but it's easy to forget that stuff because it's been 10 weeks of craziness in chemistry. So very important to remember that if you see an element by itself and it's not part of a compound, its charge has to be 0, right? Same thing over here for hydrogen. Hydrogen is an element, so its charge must be 0. If it had a charge, we would have written a number there, right? But because it's an element, there must be the same number of protons and electrons. Also, in H2, H2 is a covalent compound. Covalent compounds don't have charges, right? Now, HCl is a special compound. It's called an acid. An acid split into these pieces as if they're ionic. And so this hydrogen has a 1 plus charge in the acid. So now what we can do is we can say, okay, let's look before and after. So we're going to start with magnesium. I'm going to look at magnesium's charge before and after. What has happened to magnesium? Well, it started with a charge of 0, but then it ended up with a charge of +2. So I'm going to write that down here. So magnesium with a charge of 0 became magnesium with a charge of +2. What happened to it during this process? Well, in order to get from 0 to +2, you have to remove 2 electrons. In other words, you're losing 2 electrons. Well, up at the top there, oxidation is losing electrons. So magnesium was oxidized. It underwent oxidation. Now you can do the same thing with hydrogen. Hydrogen starts with a plus charge, and when it's done, there isn't a charge. So we'll write that. And I'm going to write it like this, just so the equation balances. Now, in order to get from +1 charge to 0 charge, each hydrogen gains an electron, and there are 2 of them. So the electrons do get conserved. We're balancing electrons as well. Magnesium lost 2 electrons, and it ended up giving 1 electron to each hydrogen. That's the process that went on here. Well, since I gained electrons, this is a reduction. Now, if I look at chlorine, you'll notice that for chlorine, oops, I don't have to do that. There we go. Chlorine starts as -1 and ends as -1. So nothing happened to chlorine. It was neither oxidized nor reduced. But magnesium was oxidized and hydrogen was reduced in this reaction. So that's what's meant by an oxidation reduction reaction, is if we break everything down into its ions, you can see that some substances gain electrons and some substances lose them before and after the reaction occurs. Now, that's really difficult. This is the most difficult oxidation reduction I'm going to give you. What we're going to try and do is we're going to try and simplify this a little bit. And the way that we're going to do that is we're going to look at structures that typically contain oxygen. And the reason we're going to do this is because in biochemistry, most of your reactions are going to be dealing with organic compounds. And the easiest way to oxidize something is to oxygenate it, really, right? That's where the word oxidize comes from. Add oxygens. So we're going to look for these conditions. If I add additional oxygen atoms to a molecule, or I bond an oxygen to a carbon additional times, so more times than it started with, then what we will observe is oxidation. Now, how does that work? Let me show you a picture here. On the screen, you're seeing organic structures, which we haven't really talked about. We won't talk about that until 131. But what this little point here means is that it's actually a carbon with enough hydrogens to fill its octet. So this dot right here, is actually this carbon right there. R is just anything you want it to be. R is just a generic label. Now, don't worry about these reaction conditions. We don't give a shit about the reaction conditions. But when I do the reaction here, the result is that I have an oxygen that is bonded to my carbon one time. Later, after the reaction occurs, I now have this carbon. I still have my oxygen bonded to it one time, but I have now added an additional oxygen. So this becomes a matter of, oh, look at the product. Are there more O's? If so, oxidation. Now, sometimes you won't get more O's. Sometimes you will just make more bonds. So here I have one bond to an oxygen. Now I have two bonds. And that's good enough for our purposes. Now, to transcribe this molecule... Oops, sorry, I lost my pen. To transcribe this again, we'll go R1C, R2, OH. Now, there are supposed to be 4 bonds to every carbon, because otherwise I don't satisfy the octet rule. So there must be a secret H, and there it is. In organic structures, H's are not drawn. You're going to fill in all the H's you need to reach the octet rule. On this structure on the right, I already have 4 bonds coming out of it, so the only thing that I need to add is this carbon. It's a weird notation that makes a lot of sense once you start doing it, because it's really easy to just start, instead of drawing this molecule, I can literally just go do. There you go, it's done. You could draw it super quickly, so that's why we do it. All right, so that's oxidation from a graphical perspective. Did we add O's, or did I make more bonds to oxygen? Those are oxidation. Naturally, reduction should be the opposite, right? I take away O's, or I make less bonds to oxygen. And that's exactly what's going on here. Let me erase this so you can see that text. There you go. All right, I don't know why it says we added H's already. My animation must have bugged out there, but that's okay. Here's another reaction. I've already drawn in all the carbons and the H's here. There are 2 ways to reduce things. So one of them is what we just said. You can get rid of the oxygens or break apart those bonds to oxygen and make fewer of them. But we need to replace the bonds with something. And the thing that we replace them with is hydrogen. Now, the reason that hydrogen is good at being a reducer is because its electronegativity is low, and the electron it brings, it doesn't really have an attachment to. It will just pass it along to whatever it's bonded to. Here, have this electron. I'm giving it to you. So in this reaction right here, we have one bond to an H, but then I do the reaction and I end with 2 bonds to H's. More H's means reduction. Now, I've actually also done that over here, too. It's just a little less obvious. The 2 became a 3. But really, all you need to do is find one instance of it, and it's a reduction. All right, so what I want you to do is, looking at these graphical problems right here, I want you to tell me, is it oxidation or reduction based on the product that you see? Okay, so look at before, look at after. I'm going to label these reactions 1 and 2. And then reaction 3 is special. Tell me which one was oxidized and which one was reduced in the reaction down there. Go ahead and type your answers in the chat. I'm going to give you like 2 or 3 minutes to puzzle this over, and then we'll talk about it together. One more minute, we'll go over the answer. All right, so in number 1 here, so you can see here's my carbon in both cases. So I've made all these bonds to oxygen, and I ripped off all these H's. So this is an oxidation. Now, these reactions are not balanced, obviously. Organic reactions tend to not be balanced for whatever reason, because we care more about what the results are. We could balance this out and write the H2O after this, but generally speaking, we don't care about water. And that's a weird sort of habit that we just do in organic chemistry. It's like, okay, we're going to assume it can be balanced and just write the products that we observe. Over here, here's my carbon. I have 2 bonds to oxygen. And afterward, I have changed that to 1 bond to oxygen. Or in other words, I have reduced it to 1. So this is a reduction. Later on, you can tell oxidation and reduction reactions just by looking at the reactants. For example, if I'm oxidizing something, I'm adding oxygen to it as a reactant. This is a common reducing agent. Sodium borohydride is often employed to remove oxygen bonds or even oxygens. And those are things you pick up in OChem. So if you take 131, you'll see some of these again. Down here, here's my iron. Iron was bonded to a lot of oxygen, but now it's not. So iron got reduced. Now, what was oxidized? Well, carbon didn't start with any oxygens, but all the oxygens got thrown on carbon. So carbon got oxidized. And there you go. That's how we do oxidation reduction. So we're going to stick to the simple method. And let's see here. Is it time for a break? Are we at break time? Yeah, it is break time. I don't know if there is a question about the more complicated method, which we did over here. I'm going to go look that up during the break real quick. But when we come back, we will continue and I'll have the answer to that question. All right, so I'm going to start the timer, and I'll see you in 10 minutes. All right, we are back. Oh, I gotta turn the music up. Sorry. So I looked at the quiz questions, and it looks like the questions are just multiple choice. But something I do want to point out, because there is a question about this, is that oxidation reactions and reduction reactions go together. So if I go back to the previous page here, and we look at this reaction, for example, up at the top here. So we said that this was oxidized. And that's true. Now, for something to be oxidized, that means that it has to lose electrons, and something else has to gain them. What must gain the electrons? Well, it must be the other thing that's involved in the reaction. So here, we would say that the oxygen got reduced, because this carbon lost its electrons to something, and that something was oxygen. Down here, we could do the same thing. So we could say, okay, well, this was a reduction. What got oxidized? Oops, wrong tool there. And that would, oops, wrong pen, there we go. That would have to be this. Oops, oxidized. So in the multiple choice questions that you're going to see for the oxidation reduction, you're going to see an equation, and it's going to say, what was oxidized? And you're going to have to tell me which element. And you're going to have to say which one was reduced, and you'll tell me which element. And it should be pretty straightforward what the answer is. And then there's another question, which is just general, like, what happens when you oxidize something? And then when oxidizing is losing electrons. So I basically told you the answers to that quiz question. All right. In your textbook, the rest of that chapter deals with this that we just did. We're not going to worry about it. I just showed you that so that you can have seen it. And then later on in cell bio, when you start talking about photosynthesis or electron transport, you can be like, oh, okay, this is how this is happening. It's an oxidation reduction reaction. And so when you do electron transport, you're moving an electron along. So you're giving the electron to the next thing. So you're oxidizing the previous thing and reducing the next thing in the sequence. And you just do that over and over and over and over and over again. And that's really all I care about for that. All right, the next section, what we're going to do is we're going to talk about energy. When reactions occur, energy is required. How do we represent that in a way that we can, like, communicate to other people, like, oh, this is what's happening? And that's where the energy diagram comes in. So that's what we're going to talk about. First of all, let's talk about how reactions occur. If I want to make a reaction, and we saw this in a video before where I had sodium and chlorine, I need my two things to bonk into each other. Now, in the video that I showed you the reaction between sodium and chlorine gas. And what we did was we heated up the sodium so that it was hot and it had energy. The chlorine in the container was something like this. So I'm going to just put little dots down for my chlorine. And my chlorine is bouncing around all over the place because that's what gases do, right? They move in their container and they rebound off of other things. If I put the sodium in, so here's my ladle, and there's the sodium. Anything that bonks into it can cause the reaction to occur. However, there needs to be enough energy, or else all that will happen is these two will bonk into each other and nothing happens, and there's no other result. They don't have enough energy to cause the reaction to occur. So the heat that we added provided the energy for this to happen. Now, alternatively, we could have heated the chlorine gas up until it was really hot, but that's probably dangerous. You don't want to heat a sealed container with chlorine in it. Generally not recommended, right? Don't heat up gases in containers, they will explode. Now, what we're going to do is we're going to look at reactions that may occur or may not based on some factors. And the first factor is energy. In order for a reaction to occur, you must have a minimum amount of energy. This is called the activation energy. If you have a matchbook or a book of matches, matches have an activation energy. They react very readily. They burst into flame, and then they burn the wood that it's attached to until there's no more wood. However, matches don't light on their own. If they did, they'd be very dangerous to have in a box stored in your kitchen. You'd burn your house down, right? In order for your match to light, you must give it activation energy. And the way that you do that is by scraping it across the side of the box and providing friction. When you provide friction, the surface of the match rubs against the surface of the matchbox, which generates heat. And that's enough energy to start the reaction. And then the match sparks, and you have fire. So you need enough energy for the reaction to start. Otherwise, it doesn't. Now, the second point that we have is orientation here. And we're going to talk very briefly about orientation, I think. Let me see. But it's not really a focus of this class. Let me see if we have a picture for orientation. I don't. We're just not going to care about orientation. Don't worry about that. Basically, if I have a reaction where, like, I'm reacting the chlorine part of the substance, and my molecules bonk, but the chlorines aren't touching, then that's just they just bounce off each other. They wouldn't react. So something like this. So if I was reacting something with chlorine, and I wanted to make this, which is Cl2, if my other chlorine came in and hit from this angle, it would just bounce off because it wouldn't see the other chlorine. But if it hit over here, the reaction would occur. So that's what's meant by orientation, is that not 100% of the reaction's collisions will result in a reaction occurring. We'll talk about that a little bit in more detail when we get to the kinetics part, which is at the next section here. But for now, let's focus on the energy part. Sometimes when you do a reaction, energy is released. So going back to the match example, if you strike a match, energy is released in the form of fire and heat. Matches are very hot. We use them to catch other things on fire, right? Now, the reason for that is because the reactants and the products of this reaction, so this would be, the reactants would be the wood and the match head, which has all the chemicals in it to start the reaction. So like sulfur and phosphorus and stuff like that. They have lots of energy. But when the reaction is done, the products that I get are ash. I get carbon dioxide. I actually get water vapor and stuff like that. These are not things that have much energy. You don't burn water. You don't burn CO2, and you certainly don't burn ashes to get energy, right? So we could say the reactants have more energy, and the products have less energy. And so what we'll do is we'll just rank them like this. So we'll make an axis. The higher up they are, the more energy they have. On the x-axis, we're going to do this. We're going to call this bottom thing reaction progress. You may see the words reaction coordinate. It's the same thing. So when I start the reaction on the left in the reactants, I have all the energy. When I have the products on the right, I have no energy. The energy has been released. And then all I do is connect the two. Now, if I did something like this, this would imply that all my reactants will just dump all their energy and become products. But we need an activation energy to do that. And so what we're going to do is we're going to change this just slightly. We're going to go like this, and you'll see what I'm doing here. Whoop. Now, I put a hill in the way, and what I'm going to do is we're going to go... Oops, we're not going to do that. We're going to go to this. I'm going to put this back on the screen so you can kind of see it. I'll just make it smaller here. And what I've made is called an energy diagram. The energy diagram shows us how the reaction behaves in terms of its energy. Now, let's suppose that I had... Here's my reactants, and here's my products. Oh, I wrote the wrong letter. Let's suppose that my curve looked like this. Now, you may have seen in this class and like the videos that we've shown where you just mix two things together and the reaction immediately occurs. There's nothing stopping it. You can think of an energy diagram as a sort of hill for the reaction. If I put a ball on this hill, there's nothing stopping it from going down and sitting here, right? So the reaction would occur immediately. So this would be an immediate reaction. And the reason for that is there's nothing stopping the reaction from just going on its own. It just reacts. Now, the diagram that we drew had a little hill in the way. So here's our reactants, and here's our products again. And we have this little hump. In order for the reaction to occur, I have to provide this much energy for the reaction to go. In other words, if this is my reaction ball, we'll call it, I have to push it up the hill and provide the energy to get it to the top before it will roll down on its own to go to the products. So the diagram shows you the relative energy between the reaction, or the reactants and the products, as well as the activation energy required. Now, I put in this much energy. How much energy do I get out as a result? Well, I would get from where the reaction begins, which is up here, all the way down to this much energy, right? So in other words, this is the energy I get back. I'm going to subtract out the energy I paid, and the remainder of the energy is the energy that the reaction generates. So this would be the fire from the match, or the heat radiated by it. Now, the term that you might see for this is called delta H, or enthalpy. These are thermodynamics terms that are used in other courses. Various textbooks use these terms, and I'm just presenting them here so that you have seen them. So if somebody says, oh, here's the enthalpy of the reaction, it's how much heat or other energy that you get out when the reaction is done. So the heat that we get, or the energy for a reaction, is the difference between the reactants and the products. And in order to start the reaction, we also have to provide the activation energy. Once we've done that, the reaction proceeds on its own. And so that's how you generate the energy diagram. All right. So this is the reaction that we were looking at. I'm going to mix two things together, and when I mix them, heat is produced. Energy is released. So my diagram should look like what we just discussed. And so here's that again shown. Since I released energy, my reactants must have more energy than the products did. There's the heat that we've released. That's the activation energy that we needed. So for a reaction that releases heat, and we'll write that on the screen here. You'll get a diagram that looks like this. Now, do all reactions release heat? And the answer is no, some of them don't release heat. For instance, if you've ever had a cold pack, when you break the seal on a cold pack and you shake the container to let the stuff mix, it gets really cold. So heat is actually being absorbed by the reaction. So if that's the case, we need to change our diagram. It's going to look different, right? Now, you might remember from Chapter 7, we had a term for this when heat is released or energy is released. We call this exothermic, right? Now let's consider an endothermic reaction. Now, if heat is absorbed, instead of having heat as a product, it's instead a reactant. Some reactant plus heat equals reaction. This would be the sort of thing like trying to heat up water and turn it into a gas. That's not a reaction, but it is a process that absorbs heat. So if I did something like this, not a reaction, but we could still draw a diagram for it. So let's do that. So we'll scroll down. Oh, I'm not going to scroll down. I'm out of space. Now, I think everybody would agree that that's too small. That's not what I was intending to say. Well, there we go. I think everyone would agree that water has less energy than steam, right? Water at room temperature won't hurt you, but steam sure as hell will. It has more energy. So if I provide the heat, which would be the difference in these two, I would then generate steam. Now, I really don't actually have an activation energy because there's nothing that really happens after it's steam. It's just steam, right? But if this was some reaction where instead of water and steam, I had two substances mixing together and the result was that product, then there may be an activation energy involved here. So this type of reaction requires us to add heat into it, and so we call it endothermic. So an endothermic graph looks like this, where the products are higher in energy than the reactants. The exothermic is the other way. Both cases are going to have a small little hump, which would be the activation energy. All right, so that's energy diagrams. So what I want you to do is I want you to try and draw a picture for the cold pack situation. So I want you to draw the energy for my cold pack. I'm going to mix my cold pack chemicals together, and the result that I feel is cold, 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 cold. Where does the heat go? Draw the activation energy diagram. So I'm going to give you 3 or 4 minutes to draw that. Obviously, you can't paste a picture into the chat, but we'll go over the solution together in just a bit. One more minute, we'll go over the answers. All right. So, let me get this on the screen here. So, hopefully you drew more or less the same thing that we just had on the screen here. So, if my reaction is I'm mixing A and B, and what I feel is cold as a result, that must mean that heat was absorbed. Because if it was hot, I would feel it, and the hot would go on the product's side. But if heat's being absorbed as a reactant, then what you'll feel is cold. So that means that our reactants will be lower in energy than the products. And we can draw a little hump in the middle there. Here's our activation energy. This is probably much taller than it needs to be, but that's okay. And then this would be the heat absorbed by the reaction. Now, because the reaction absorbed the heat, heat went into the reaction. This is an endothermic reaction. And we already put heat in our equation, so we're all set there. So there's the solution. All right. On the quiz, what you're going to be doing is you're going to be given an energy diagram. You're going to have to tell me which part represents the energy transfer from the reaction. Did the energy come in or out? Was it exothermic, endothermic, etc.? I'm going to draw the picture for you, and you'll have to identify features on it. Like you'll have to click on the activation energy or something like that. All right. Now that we've talked about energy, let's talk about how fast reactions can go. Because if you heat a reaction up, shouldn't it go faster and faster and faster and faster? Sure. But are there other things you can do? And there totally are. On the screen, I have two reactions. One is explosive. The other is super, super, super slow. You don't make something out of metal or steel and then it immediately rusts in front of your eyes. It takes quite a while of neglect and lack of use, right? Eventually, metal will become rusty, but it doesn't happen immediately, thankfully. That means that we can use the metal in the meantime and not have to worry about corrosion. Dynamite, on the other hand, happens instantly, and we kind of want it to do that, right? We don't want dynamite to take 30 years to blow up, because that would be a very, very slow reaction, and we couldn't harness all the work. The whole point of dynamite is to blow things up so that we can destroy whatever's there and move it out of the way or build in that space or whatever. So, like, dynamite is used to, like, clear trenches or knock down old buildings that aren't used, etc. So, understanding why reactions go fast and why others go slow is important. And so this is called kinetics. Kinetics is a study of reaction speed, also known as the reaction rate. How many reactions occur per second, or minute, or hour, or whatever. Reactions being like collisions. So what we're going to do is we're going to study different ways that we can control how fast a reaction goes. And the point of this is so that we can understand, okay, if this makes the reaction go faster, but I don't want it to go faster, what are my options? For example, in medicine, you do not want all of your medicine to be absorbed by the bloodstream at once. That could be toxic and cause you to die. So we need to affect the rate. That's where things like slow release caplets come in. How do I make the reaction go slower? Well, I lower the amount of medicine that's there by releasing it more slowly. That would be point 2 on here. So we're going to look at these 4 different things. Physical nature, i.e., what does the substance look like that we're manipulating? How can we change its state? Like, can we grind it up, or can we cut it into smaller pieces, or can we form it together into one big piece? That sort of thing. We're also going to look at concentration, which is the amount of stuff that is present or available. Temperature we already talked about. And then catalysis is a special case that we'll talk about at the end. So let's do these one at a time. And for most of these, I have videos that I'm going to show you. Now, in order for things to react, they have to bump into each other. I have to have A and B contact each other in order for a reaction to occur. If I don't have very much area to contact, my reaction won't be very fast. So in this case, and I can't see it on my monitor because my contrast is weird, but you can see right here, I have this liquid surrounding a solid. So the liquid is B, and the solid is A. Now, where can the reaction occur on A? It can only occur on the surface, right here. Now, if A is just a giant cube that I dropped in there, I get its surface area and that's it. But what if I ground A into smaller pieces? Well, I'd still have the edges that I drew in before. So this is all the same length of black that I drew on the previous diagram. But now I get to add in additional surface area that the reaction can occur on. So by grinding this up into a smaller chunks, we'll say, the surface area increases, and there are more opportunities for A and B to interact with each other. So, which will go faster? A big solid chunk of A, or tiny pieces of A immersed in the solution of B? And you don't have to type it in the chat. Obviously, the one with more surface area should react more quickly because there are more opportunities for collisions to occur. And so we can see this in action. So what I'm going to do is I'm going to give you a video, and what I want you to do is tell me, of the 3 solutions that we're going to look at, which one has the most finely ground calcium carbonate, and which one has the chunkiest calcium carbonate, based on what you see. So let me get the video ready here real quick. Okay. We don't need his voice, but we do need this. And there we go, perfect. All right, so I'm going to hit play. And we're going to dump one of the dishes into the container. So here's the first one. There it goes. You can see the reaction occurring because it's bubbling a little bit. It's kind of hard to see the bubbling, though. All right, here's the second one. Faster or slower? And what does that tell you about the stuff that we poured in there? In fact, you can kind of see it, right? All right, here's the third one. So as you can probably very clearly see, the one on the left reacted way faster and is way foamier. Over here, you can see that going. The one in the middle is going kind of fast, and the one on the left there, oops, I don't want it to fade out, I actually want it to stay on screen. The one on the right is going very, very slowly. Now you can see the chunks of it on the right, and you can see a few grains of it in the middle, and over here it's just a fine powder. And I think, if I zoom in the video here, he'll actually show us that. So this is a fine powder. There you go. You can see that it's little tiny chunks here. This one is much more chunky. It's actually kind of hard to see those two. This one is very clearly chunky. So the more surface area there is, the faster the reaction goes. All right. Let's talk about concentration. In order for a reaction to occur, again, you need your substances to bonk into each other. Now, if you have lots of one substance, you have more opportunities to bonk. So for instance, let's say in solution 1, I have 1 mole of A and 1 mole of B. But in solution 2, I have 1 mole of A and 4 moles of B. And my reaction is going to be A plus B makes whatever. Since there's way more B in the solution, I have more opportunities for a reaction to occur. Because if I look at one molecule, just say A, and there's an equal amount of A and B in the solution, and I choose a molecule to bump into randomly, half the time I'm going to run into another A and nothing happens, and the other half of the time I'm going to run into another B, and the reaction will occur. So over here, this will be a reaction, but this won't. So I have a 50% chance of a reaction occurring if I bump into a reactant molecule. But over here, I have a way bigger chance because I have way more B's than I do A. So there's an 80% chance of a reaction occurring here. So the overall speed of the reaction goes up. There are more opportunities for the reaction to occur. Now, I've sort of simplified this because there is another substance in the container, and that's water. And there is way more water than everything else. So the odds of a reaction occurring are not exactly like 50% or 80%. They're more like 0.0000001% and then 0.00004. But the point remains that if I just exclude all the water, the more of a reactant that I have, the more likely it is to collide, and the faster the reaction will go. So that's concentration. You have more stuff, the reaction occurs more quickly. Easy as that. No video for this one, unfortunately. Now, for gases, pressure is related to the amount of stuff that's in there. So if you have a higher gas pressure, the reaction will go up, or in terms of its speed, its reaction rate will increase. So when we administer oxygen to people who have a hard time breathing, the reason that we use pure oxygen, or at least a higher concentration of oxygen, is because the rate at which their lungs are collecting oxygen is too low, and we need to speed that up. So we just increase the amount of oxygen in their lungs, the amount of pressure. That increases the rate at which oxygen is absorbed for those people, and so when they are on oxygen support, they can then function normally. They have a sufficient amount of oxygen because we've just given them more. The third one we'll talk about is temperature. How does temperature affect how fast a reaction goes? Well, temperature is just how fast a molecule is moving. So at low temp, Molecules move slowly. At high temp, molecules move more quickly. Since things that are moving have kinetic energy, try rolling a ball into the wall and then throwing the ball into the wall as hard as you can. Which one hits the wall with more force and more sound? The one where you throw it faster, right? The faster something is moving, the more energy it has. If a molecule has more energy, then it's more likely to react because it will be able to overcome the activation energy. So as temperature increases, the reaction speed also increases because a larger number of particles have enough energy to overcome the activation energy. And we can see this in action here. I'm going to show you two glow sticks. One of the glow sticks will be immersed in cold water, and the other glow stick will be immersed in hot water. Here's our glow sticks. Now, they should have the same brightness, and you can kind of tell from the middle here. There's a little bit of an artifact with the camera. This one looks a little brighter on the left to me, but look in the middle, and they should have the same brightness. We're going to submerge them. One will go in a cold bath, and one will go in a hot bath. Which one is which, based on the results of this experiment? So there's bath number 1, and there's bath number 2. And what I'm going to do is I'm actually going to tab this forward a little bit. So we'll go like this, and you should be able to see the results pretty quickly. And we'll leave them in the water here, actually. Okay. So which one was the hot water and which one was the cold water? And which one had enough energy to prolong the fluorescence reaction? And which one did not have enough energy to have as many molecules produce the fluorescence effect? And you should be able to tell the one on the left, oh, it's very bright. The one on the right, not as bright. When we take it out, you can see the difference here once the camera equilibrates to the amount of light there. So the one on the left, that was obviously the hot one. The one on the right, that was the cold one. So that's cool. So we can play with temperature and affect how fast our reactions go. If we want a reaction to go faster, you heat it up. If you want it to go slower, you cool it down. Easy enough. The last one that we're going to talk about today is a catalyst. A catalyst is a very important biological substance. Not necessarily biological, I should say. So in biology, we use catalysts all the time, but you can use catalysts in regular chemistry as well. And the features of a catalyst are the following. The first feature is that it makes reactions occur more quickly. In the presence of the catalyst, the reaction will go faster. But the second property is that it is not used up in the reaction. What that means is that you can use it effectively forever. An example of this is the catalytic converter on your car. What that does is it helps break down waste products from your exhaust from the engine into carbon dioxide and nitrogen. Now, the reason that we need this is because when you burn stuff in your engine, you often get nitrogen oxide products, also known as smog. When nitrogen and oxygen combine, you get this brown gas, which smells bad. It contributes to air pollution, and obviously we don't want that, because that will pollute our environment and make our city smoggy and the air quality is poor. So what the catalytic converter tries to do is that when the exhaust gas passes over it, it speeds up the breakdown of smog into nitrogen gas, which is already in the atmosphere, and oxygen or carbon dioxide gas, which are also present, or the products that are less harmful. Now, nitrogen gas will, smog will eventually break down into nitrogen and oxygen, but it's very slow. But by hitting the catalytic converter, it does it very, very quickly. So here's an example of an uncatalyzed reaction. So we've seen this already. This reaction requires lots and lots of energy to activate. But if I add a catalyst, what happens is that I provide a new reaction pathway, and I get a new energy diagram. And the result is that I need a lot less energy. So the way that this happens is that catalysts lower the activation energy. And when the activation energy is lower, more molecules can then react at whatever temperature or whatever conditions you're working at. So let's see that in action. This reaction is hydrogen peroxide. This happens in your hydrogen peroxide bottle that you have stored underneath your sink or in your medicine cabinet or whatever. Hydrogen peroxide will decompose into water and oxygen gas. However, it decomposes very, 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 very slowly. Light will cause it to decompose. Heat will slowly cause it to decompose. And that's why we store it in a dark bottle to prevent that, so you can keep the peroxide and use it for cuts or whatever it is that you do. Now, if we wanted to react this much more quickly, we can add a catalyst. The catalyst we're going to use is sodium iodide. And we're going to do that in this demo here, which was done on Jimmy Kimmel some time ago. And this will probably get me a copyright strike, but I'm going to play it anyway because this is probably my favorite video to show. All right, so we're going to turn on the audio, and we're going to put this here. All right. Please don't strike my channel, Science Bob. This is for my students. So here we go. We're going to add the hydrogen peroxide into these giant beakers. We're going to then add dish soap to catch the oxygen bubbles coming out. We're going to add a dye to make it pretty, and then we'll add the catalyst. And here we go.
We're going to start with a little bit of actually dish soap. So if you want to put some dish soap in your flask.
How much? Just a squirt?
Yeah, a little more. That's good.
Okay.
So dish soap will keep the bubbles because we're going to remove the oxygen. They'll hold the oxygen.
Okay.
So I'll put a little bit in here. All right. Next, coloring. We have green and red. Do you have a preference?
I'll take red.
All right.
It's be very Christmassy. How much of this?
And just keep going. Keep adding a lot of that.
Okay.
That's good. A little more.
This is going to be delicious.
All right.
Is this how you did your jacket?
So one thing I want to comment on that I think is really funny, every time they add a liquid, music plays. And I kind of wish that that's something that would happen in my life. Every time I pour liquids, just music.
That's good there.
Okay.
All right, so I'm going to add the hydrogen peroxide because you don't want to do that.
Okay. Oh, it's dangerous, right? Okay.
And actually, yeah, let's get all geared up here.
Okay, good. Put these on my eyes.
There we go. All right, so in goes that. And
Now, what's happening here? What process are we about to see?
So here's what we're going to see. We're going to, in order to remove the oxygen, we're going to use a catalyst.
Okay.
The catalyst will speed up the reaction. So we're going to, that's what's in here. It's a sodium solution. We're going to pour that in, and that's going to remove the oxygen. The soap is going to hold it, and
we're going to smother to death, all of us.
It'll be okay, but it will create a lot of bubbles really fast.
Okay, great.
And usually this is done in graduated cylinders, but we're going to make it a little more intense with these ridiculously large flasks.
Okay, good.
All right. So this is what you're going to use. We're going to pour that in there. The oxygen will be released, and we'll watch the reaction. We're going to need to step back after we pour it.
Okay.
All right. Here we
Step
go.
back.
Ready? In 3, 2, 1, pour. There we go.
Whoa! Whoa! Wow, that's great. It's like Ghostbusters. Wow. Whoa! That's something.
And it went so high it actually got caught on one of the overhead lights of the production. But that demo is called Elephant Toothpaste. The reason being that if you put like a little stripe of food coloring down the side of the container, when it comes out, it looks like crest. And I do that demo for 5th graders every spring, and I would actually be doing that probably tomorrow or Wednesday of this week, or maybe next week, if we were meeting on campus, but alas, we're not. So I don't get to invite you all to come see it as much as I would like to. So maybe next year when I'm on campus, we'll get to do that. All right, so those are the 4 features that govern how fast a reaction goes. So again, we can look at surface area. The more surface area something has, the faster the reaction goes. The more stuff you have, or concentration, the faster the reaction goes. The hotter the reaction is, the faster it goes. And if you put a catalyst in, the reaction will go faster too. All right, so I'm going to leave these questions on the board for you to answer. We're out of time for today, so we're going to answer these questions at the start of tomorrow's lecture. But what I want you to do is consider all the types of reactions that we studied. And the first question actually wants you to invert all that. Hey, I'm putting milk in the refrigerator. Why do we do that? Well, we don't want milk to react, right? We want milk to stay fresh. So what are 2 reasons we store milk in a tightly sealed container in the fridge, as opposed to like just pouring it in a bowl or something? So think of 2 reasons. We'll come back to that tomorrow. We'll talk about it. And then for the second example right here, I have a specific reaction with a powdered chemical. The reaction only goes 10 minutes. What can I do if I want the reaction to go faster, i.e. speed up? And what would I do if I want to make the reaction last longer, i.e. don't go as quickly? Okay. I'll leave that for you to consider tonight. In the meantime, make sure that you get quiz number 7 in. The deadline for that is tonight. That is a soft deadline. Quiz number 8 and worksheet number 4 are both due tomorrow. That is a soft deadline too. But that's a lot of stuff coming up, so just make sure that you are staying on top of it and you get it all in by the deadlines. I want to thank everyone for coming out to the lecture. Go out and enjoy the rest of the sun. And I'll see you tomorrow. Have a good night.